Okay, we're going to come back into chapter 3, starting with plasticity. Okay, two terms here that there's not one in the book, but elasticity versus plasticity. Really quick. Plasticity is the ability of a material to deform without breaking. Okay, so that means it stretches, it's deformed, but it doesn't break. So just like you can draw it out like Play-Doh or putty, it'll stay in that shape, but it didn't break. Now elasticity is important to where it's like a rubber band. If you stretch it, not too far, but to just within a normal distance, it will go back to its original shape. Okay, so it's elastic. It goes back to its original design. Metal has elasticity as well. Very short, little amount, linear amount anyway, I should say. But it does have elasticity. Once the metal has been stretched beyond the elastic point is when it becomes plastic. So once it's deformed, now it's in the plasticity stage. Okay? So it's deformed, it's not going to go back to its original shape, but it didn't just break. Okay, it's important. Most of us know that, you can hit something or hammer on a piece of metal, it'll indent. It can be manipulated, but it didn't just fracture or crack in half like you would with maybe a ice cube or something, okay? Or possibly cast iron. Strength. It's the ability of a material to resist deformation, usually expressed in ultimate tensile strength in pounds per square inch, okay? Strength can be to resist deformation or to carry a load, an applied load. Toughness. Toughness has high tensile strength and ability to deform permanently without breaking. It's the opposite of brittleness. One way that I keep toughness in mind for me, to remember what the definition of it is I think of a boxer. He can take plenty of punches, but he keeps going. He's very tough. Okay, he doesn't just falter after one hit. A very brittle steel that does not have any toughness, if it takes one impact, it doesn't deform, it just snaps in half and falls down. Okay? Impact resistance, the ability of a material to withstand a maximum load applied suddenly. It is also associated usually with toughness. Toughness can have different values within it as well, whether it be surface conditions, if there's a notch in it, then that's notch toughness, impact strength, and so forth. Moving on, brittleness. Fail without any warning as deformation, just like we talked about, the opposite of toughness. Okay? Malleability is the ability to deform permanently under compression without breaking or fracturing. The actual definition is the ability to be drawn into a wire, okay, without breaking. Hardness, that you can be measured. It's the ability to resist indentation, okay. We do have hardness testers in the shop. There are several ways of checking it, whether it be from a Bernal hardness test, a Rockwell, or a Vickers and Knoop even. We talked about elasticity and the elastic limit. The elastic limit is the greatest amount of load that can be applied before it turns to plasticity. Okay? The modulus of elasticity is a ratio of stress to strain. Yield point. Yield point is the point at which definite increase in length of specimen occurs and no increase in load. So, you can say that the yield point is also fairly comparable to the point between elastic and plastic. Because right here it says the point at which definite increase in length of specimen occurs. So that means that once it's become deformed, that's what we're looking at. So when we talk about yield point, For example, a common steel, mild steel, A36 steel, has to have a minimum yield point of 36,000 pounds per square inch. Its tensile strength might be at 60 or 50, but it has to have a minimum yield point. So every piece they test, they take it up to 36,000 pounds. It has to go back to its original shape and no deformation whatsoever. Okay? Ductility of ability of a material to be permanently deformed by loading and yet resist fracture, so it doesn't break. Corrosion resistance, I want you to read through these on your own. Carbon and phosphorus. We're starting to get into the common elements of steel. Okay? Low and high carbon steel, boron, silicon, sulfur, selenium. See, some of these improves the machinability of steel, increases the hardenability. Silicon, added as a deoxidizing agent to produce sound well during steel making. Phosphorus. Small amounts improve machinability of low and high carbon steel. Manganese. In the pure state, it can scratch glass. Okay. Very resistant to abrasion, used in equipment such as rock crushers, grinding mills, power shovels, scoops, so forth. So, exactly what we've been talking about. There's some toughness there, right? So we can add a little bit of manganese to a normal steel, and we've increased its toughness. All right. Molybdenum increases the corrosion resistance of stainless steels. Chromium, it's known for its corrosion resistance. Stainless steels have to contain at least 12% of chromium. By general standards, what they say is 12% chromium to be a stainless steel. There are just a couple new cases of stainless steel out there to where they're like a 9% or 10%. However, most tests across all of the trades are going to ask you, they must contain at least what percentage of chromium to be stainless steel? The answer is 12%. Okay? Nickel increases strength, toughness, and corrosion resistance. Has very good properties. Excuse me. Has very good cold weather properties as well. Okay. Low temperature capabilities. Cobalt, titanium, zirconium. Feel free to read through these on your own. Here's something that I think most people don't realize, that aluminum itself is an alloying element. Okay, it's not just, it's an element. It's not just its own material. It's used in carbon and alloy steels quite often. Produces a fine grain structure. It can help with some corrosion resistance to normal atmospheric air as well. Has good ductility. Lead. So forth. Alright, let's get into the carbon steels. So we're going to talk about 4 different types of carbon steels. We're on page 86 in the book, Types of Steel, Carbon Steel. I want you to highlight the headline of every one of these, okay? We're just going to run through the PowerPoint real quick. Low carbon steels are usually do not exceed 30%. Okay? They're referred to as mild steels. Mild low carbon steels. Excellent weldability. Most structures, bridges, ships, tanks, and pipes. Medium carbon steels usually have a carbon content ranging from 0.30 to 0.60%. So we're talking less than 1% carbon by weight. Okay? 0.30% to 0.60. Stronger, higher heat treating qualities, better capabilities for certain things. T1 type of plate, it usually falls within your medium carbon steel. for something that might see a lot of structural or vibration resistance as well. Okay? If you look down here on the bottom, medium carbon steels, best results, usually you want to preheat them, at least sweat and get the moisture out of it before you weld it. And then you can let it cool off on a normal situation, normalizing. High carbon steels. They range from 0.60 to 1.7%. Can be heat treated for maximum hardness and wear resistance. They're usually used, good example there on the bottom, punches, dies, tools, military tanks, and structural steel. Certain places you might have low carbon steel with high carbon steel girders or support beams within it, okay? So again, if you're on a job, you can't just assume that everything's a low carbon steel. You should be looking, making sure that you're reading the print correctly, making sure that you are preheating, welding, preheating, post-heating, and welding with the correct filler metals and so forth, according to the percent of carbon of steel. Alloy steels, even normal steel is considered an alloy. However, what we're concerned with alloying is usually they contain alloying elements exceeding the normal values, okay? High strength, low alloy steels. The high strength, low alloy steels make up a group of steels with chemical compositions specifically developed to give high physical property values and material greater corrosion resistance than obtained from carbon steels, okay? Generally used when you need savings in weight. Oil hardening steels, air hardening steels, high speed steels, so some of our bits and so forth. All right. You have a really good strength factor without getting into a really heavy material, and usually you're able to sharpen them better, finer edge, they resist impact, they have greater toughness, so forth, okay? A lot of times bushings are made out of high strength, low alloy steels. Now when you're welding these two materials together, say if you, if you're welding a bushing inside of a mild carbon casting or mild carbon steel, usually you want to use like a stainless filler metal or a high grade, preheat everything really well, and then you're either going to be using 309 for dissimilar metals or a stainless steel filler metal to weld both of them up, or you would be using like a 110-18 low hydrogen with a very high tensile strength and a preheat usually of 400 to 500 degrees, okay? Stainless and heat resisting steels. Now we're going to break down the book, and I want you to highlight a few things out of this, okay? Out of the book, page 87, right hand column underneath stainless and heat resisting steels, let's read. As the name implies, stainless and heat resisting steels possess unusual resistance to corrosion at both normal and elevated temperatures. This superior corrosion resistance is accomplished by the addition of chromium to iron. Here's the bulleted item. The corrosion resistance of the stainless steel generally increase with increasing chromium content. It appears that when chromium is present, a thin layer of chromium oxide is bonded to the surface, and this oxide prevents any further oxidization, which is the ordinary rusting in most common kinds of corrosion. So right here it says 11.5. You will see 11.5, 12, right in that area. Most tests that I've seen have been 12% as the general guidelines. And it can vary a little bit as well, but for the most part, they're not going to trick you and say is it 11.5 or 12. They usually have like 6%, 12%, 18%, and so forth. Okay? Page 87, I want you to go to the right-hand column. Once you go to the very bottom, you see the two bolded items. Let's go up to the second paragraph before that, about a third of the way up from the bottom. The sentence starts out, pitting can be materially reduced. Okay, reading from the book. Pitting can be materially reduced by treating the area with strong oxidizing agents such as some chromates or phosphates. The addition of molybdenum to austenitic nickel chrome steels also helps control pitting. So this is important if you're going to be running certain chemicals within it. Also, if it's going to be a bearing type application that's going to see more wear and abuse, more susceptible to pitting as well. Gears, items of that nature, okay? So then we start into the bullet items out of your book. I would highlight all the bullet items. Okay, let's go down to the 5 classifications of steels. We're on page 88, bottom left-hand column. These are the 5 classifications. I would highlight these 5. Make sure that they're bullet items you understand. The 500 series is basically what we call martensitic. Now if you look at this, here's the example that I was telling you. It's only 5%, right? There's always exceptions. I know, they give you a general rule of thumb, and then they throw something in there like that. And that's the way it is. We didn't write it. These are the standards for across the whole entire nation, okay? 500 series is the 5% chromium, martensitic. 400 series is martensitic, but it's back up on the chromium content, so more corrosion resistance than the 500 series, okay? The 400 series ferritic. Then you have austenitic, which is a 300 series, and then 200 series is austenitic as well. What's the difference between these? So now we've got the addition of manganese in there as well, okay? So I want you to read through. Here's a 4 to 500 series of martensitic. Primarily heat resisting, retain a large part of their properties. Up to 1100 degrees. Right here. More resistant to corrosion than alloy steels. It's not considered a true stainless steel in most applications. However, it's still a 500 series stainless steel when you go to work on it. So it can be rather confusing. Just knowing it and being aware of it, you can't change it. So we might as well just be aware of it, all right? Air hardened must be cooled slowly or annealed after forging or welding to prevent cracking. Highly susceptible to cracking. So you don't do a lot of it. If you do, make sure you're wrapping stuff up, using a torch to help bring it down nice and slow, or a weed burner if you don't have electric heat blankets or a furnace, so forth, okay? 400 series. This is a good series of ferritic, so it can be, sometimes it can be magnetic, okay? Ferritic means iron, ferrite, okay? Chromium content 11.5 to 27%. Carbon contents is very low. There's no nickel in it. It cannot be hardened by heat treatment. The hardness may be increased by cold working it, okay? There's a very low coefficient of thermal expansion, so less growth. Good resistance to corrosion, fair ductility, difficult to weld. 200 and 300 series austenitic. Your nickel can be from 3.5 to 22%. So right here, this one right here, your 400 series has no nickel. This is your 2 to 300 series. Your nickel can be from 3.5 to 22%. So let's look at the service condition that it can be within. I think I've talked to you before. I worked at a helium plant there in Wyoming where we were getting down to very, very low temperatures, okay? So nickel has great, or even the airplane industry, okay? We want some nickel within it. It has great low temperature properties. If it's a certain grade of stainless steel that I want some corrosion and nickel, this would be the series, the type of series that I would be looking for in fabrication, all right? Low yield point with high tensile strength at room temperatures. Stable structure at low temperatures as well. We just talked about that. Carbon is minimal. provide max resistance to corrosion, high rupture and creep strength values at high temperatures. So it has a good oxidization resistance. Okay, duplex grade stainless steels. Nickel's not quite as high as the 2 to 300 series. Carbon's even lower yet though. Okay, so a lot of times you're seeing a chemical process come through, like in a piping system, or maybe a chute system to where it'll wear out right next to the weld pattern. We get the sensitization along the weld toe. This might be something that we would want to, this might be the greatest stainless steel that we'd want to use. It has twice the yield strength of the 300 series. So right here, thinner sections and weight reduction must be desirable. I've done a lot of chute work out of the duplex grade because they're strong. They can handle pressure. Tool steels. Carbon or alloy steels capable of being hardened and tempered repeatedly. Okay? Produced primarily for machine tools which cut and shape articles used in manufacturing. Varying chemical composition depending upon the end use. Carbon ranges usually from 0.8% to now we're up to 1.5%. That's pretty hard. That's getting close to that cast iron range, okay? Rarely welded, must be preheated to do so. Carbon equivalency. You might see a question like this on your test. Basically what this tells you is it's intended, a variety of formulas for calculation is what's the equivalency for carbon. Intended for use of carbon and alloy steels that contain more than 0.5% carbon, 1.5 manganese, 3.5 nickel, and so forth. Occasionally you might see this, very seldom. But you start dealing with some, around here in Central Oregon, we have a very broad range of manufacturing facilities around here. Some really specialty shops, which is, again, you don't want to ever limit yourself. Just kind of being aware of what it is. We will give you the values and so forth. You can work through it on your own. Okay, American Iron and Steel Institute steel numbering system. Based on the chemical analysis of steel, number designations indicating the percent of predominant alloying element. Table 3.7 shows you the first digit of the numbering system. And table 3.7 is on page 92. I want to talk a little bit more about this. I want you to look back through the other tables as well. They talk about ferritic stainless steels, martensitic, austenitic, and so forth. Okay. I'm going to pull this off. We're going to look at the book real quick. There's a few things that I really want to talk about with the numbering system, specifically here. First digit's the major alloying, so carbon, nickel, all the way back down to 9. So to begin with, these are carbon steels. You notice the first digit with